Most folks may not understand that when you take a photo, you're using AI. When you search for something, obviously, you're using AI. Even when you pull down and look at applications on your phone, you're using AI. Increasingly now, even when you're typing on your keyboard, you are using AI. There is pattern recognition in the predictive text that you're doing. Humans are similar creatures, and I think recommendation systems have proven that over time. All of that needed to be powered by infrastructure. The world is actually quite hard for an AI engineer. It's not like you just train a model and then amazingly it just deploys everywhere. That's not actually how the infrastructure works.
Welcome, humans, to the Neuron Podcast. I'm Corey Knowles, as always, joined by the one and only Grant Harvey, who writes the Neuron every day. Today, we're going to talk AI infrastructure and whatever else comes to mind with Tim Davis, co-founder and president of Modular. It's a company that has raised $250 million to change how AI runs on hardware. Tim, welcome to the Neuron.
Yeah, thanks guys. Thanks very much for having me.
Congratulations on the raise as well. That's exciting stuff.
Yeah, I mean, I've always viewed, fundraising, is an interesting process. I'm happy to walk through it, and we have a unique methodology, I think, that we've taken in fundraising. But yeah, in many ways, it's just, we're excited that we have people who believe in our vision and what we're trying to achieve. And yeah, I'd like to talk to you both about that and other questions today.
Well, I guess to start out, you're with Modular, and I understand that you and your co-founder are both from Google Brain, right?
Yeah, so so maybe a little bit about me and a little bit about the background of the company. So I spent, it was probably 6 or 7 years at Google, a lot of that inside Google Brain. And that's actually where I met Chris Lattner, who is a, very renowned engineer. And he was brought in, to help bring up some of the TPU infrastructure, which is sort of Google's custom silicon for running AI models. Before that, Chris was at Apple, and then before that had done, a lot of other things in his career, LLVM, which is an open sort of compiler, open source compiler foundation. And so we had been working on an infrastructure platform called TensorFlow, which was one of the original machine learning and AI frameworks at Google. And Google had released that really to, provide the world with the ability to build, AI models and in many ways help, this was back in 2015, 2016, help begin to democratize AI. They had actually just acquired DeepMind at the time. And so, I independently became very excited about AI. I'd had a startup before joining Google, and, we had started to dive in more what and now is probably traditional machine learning.
Yeah.
So sort of, what folks would,
Sentiment
most simple-
analysis kind of stuff. And
Yeah, I think,
Yeah.
More traditional techniques for essentially recognizing patterns in data and predicting outcomes. And then, as deep learning began to accelerate, and so the complexity of sort of these networks that we started to build, we started working on, sort of open infrastructure for the world to help accelerate those things. And so I worked on, not only TensorFlow with an incredible group of people inside Google Brain, I also spent a lot of time looking at edge, so scaling this out to mobile phones, penetrating Android devices. So, most folks may not understand that when you take a photo, you're using AI. When you search for something, obviously, you're using AI. Even when you pull down and look at applications on your phone, you're using AI. Increasingly now, even when you're typing on your keyboard, you are using AI. There is pattern recognition in the predictive text that you're doing on your keyboard.
shopping
And
on
so-
Amazon. Yeah.
100%. I mean, humans are similar creatures, and I think recommendation systems have proven that over time. So all of that needed to be powered by infrastructure. And when you're a company as significantly large as Google, trying to standardize on a piece of infrastructure is really important. But one of the things that happened, and I think, what Chris and I started to realize when we were at Google was Google really had and it's, probably interesting for your audience. They actually had 3 stacks. And this is like full software stacks. They had a software stack for TensorFlow that was sort of optimized for TPUs, which is their proprietary silicon. They had a software stack that was optimized for CPUs and GPUs, which is now what the world would know as for example, NVIDIA machines or AMD machines. And then another software stack that was optimized really for edge devices. So think of Android phones or iPhones, or even smaller things like, microcontrollers that run around in all sorts of different, robots and systems like that. And so, what we quickly began to realize was the world is actually quite hard for an AI engineer that, believes in deploying not only in large scale data centers, but all the way out to, edge-based environments.
Yeah.
It's not like you just train a model and then amazingly it just deploys everywhere, right? That's not actually how the infrastructure works.
Yeah.
And
Right.
so I think what we realized was, well, what we really need to try to build is a platform where, maybe that future is actually possible, where you could, in some ways, abstract away all this hardware complexity. The idea that, and I think this is goes into our vision for modular, which is a unified compute layer, which I'm happy to talk about. But I think one of the biggest sort of product lessons, one of the most interesting developer lessons from our time at Google was realizing, and this will be a controversial statement, so prepare yourself, most developers don't care about the hardware.
Yeah.
Now that will
Oh,
be
that's not
in a world where,
controversial. I feel like
okay,
that's
great.
very well understood.
Great, because in a world where NVIDIA is an incredible $4.5 trillion company, it sounds weird to say that, because in some ways the construct is, well, clearly the hardware is the most important thing. Every developer that I've talked to, including myself building applications, what I care about is what is the throughput, what is the latency, what is the accuracy target, and what is my cost threshold. Once I have those, they're my inputs. Fundamentally, the hardware is sort of the output that then has to meet the requirements, and you end up having to, in some ways, be exposed to it, because you end up not having many choices actually at the end that can meet those requirements. And so we realized, well, and we can get a little bit into what we, in our thesis on the future of superintelligence, but, we strongly believed, and there was this concept at Google of what you train is what you serve. And in today's world, that actually doesn't exist. When you train a model, whether you're using PyTorch or other frameworks, you actually need to do a lot then to serve that at scale in production. It's not like it just instantly happens. And so, we realized, well, hang on a second, if we could build a platform that not only helps abstract away some of this compute, but began to work towards this vision of what you train is what you serve, then, maybe our, very significant contribution to the planet and to humanity is helping to realize this sort of vision of superintelligence.
All right. So if you're building anything in AI right now, whether it's models, tools, workflows, you're going to want to hear about this. Dell just dropped something that's honestly in a league all of its own. The Dell Pro Max with GB10. That GB stands for Grace Blackwell, which is NVIDIA's next generation architecture. And here's why you're going to care about that. This machine looks small, but it's a powerhouse. You're getting 128 gigs of unified LPDDR5X memory, super low latency, and the brand new NVIDIA GB10 module, which lets you run local inferencing on models all the way up to 200 billion parameters, which is insane. No cloud queues, no sky-high compute costs, just your own personal AI sitting right there on your desk waiting for you. And here's the wild part. If you need to go bigger, you can connect two Dell Pro Max units together using the ConnectX 7 SmartNIC and 200 gig networking to scale your workloads bigger. It's seamless, it's fast, and designed for serious AI development. Everything stays local and secure, whether you're building at the edge, handling sensitive data, or just trying to push the limits of what your models can do. Plus, it comes ready with the full NVIDIA AI software stack and DGX OS, so you get right to work. If you want cutting-edge AI performance in a compact form factor, check out the Dell Pro Max with NVIDIA GB10. It's the future, and it's already here. Check out the link in the description here to go get one today.
I feel like a lot of software, there's a famous phrase, I forget who says it, is like software is abstracting away the horrors of hardware, right? That's, have you heard
Okay.
that?
Yeah. I was just going to say, and it's an interesting observation, right? Because I think most programming languages today in the world, they're very CPU specific, right? Like it's not like Python was never truly designed to go and run on a large scale, highly parallelizable, accelerated machine. That actually wasn't why it was created. Most programming languages today were very specific on CPU related programming, because most of the world's compute was CPU. As now everything's sort of turned over and we're going through this massive upheaval of infrastructure that's spinning towards, parallelizable, acceleratable compute. What is the compute model that supports that, right? And I think that's where what we realized at Google was you really need not only a programming model that jumps on a CPU and can do everything that you want on a CPU, but that can then also carry that over to an accelerated device. And the most famous of this today is CUDA, but that is very locked to NVIDIA's systems, and they've made a bunch of incredible, progress and design decisions as to why they did that. But then it doesn't help the developer who's out there going, but hang on a second, I don't want to just necessarily use NVIDIA. I also want to use other types of silicon. There's all this new hardware being invented. There's all of this hardware that exists
I want
in
to
a
use every
phone.
GPU I can get my hands on. Yeah.
Yeah, but and it's funny, Corey, even in a mobile phone, right? Like you think about it, one, NVIDIA doesn't actually get you there, but two,
Mhm.
in a mobile
Mm.
phone, you have a CPU, a GPU, a digital signal processor, a DSP, and then an NPU. So your neural
Mm.
processing unit.
Oh, wow.
You have 4 pieces of silicon. And so again, to really unleash the power of that, to really enable people to say, well, what are these amazing applications that we could be building on mobile phones and other, devices, wearables that are out there in the world? What is the compute model? What is the platform that enables us to do that? And there isn't really a good one today, until, here's a plug, until we came around, I would claim. And that's
Yeah.
what we're building.
Do you think that we are hardware constrained on the path to AGI or superintelligence, or are we software constrained actually?
So stepping back, like what is intelligence? I would argue today, the path we're on, and I would argue I don't necessarily know this is the right path, but the path we're on today is let's keep training, according to the scaling laws, let's keep training bigger and bigger models, right? So I think Grok was trained on 5e to the 26 flops. Now there's discussion about let's go and train models on, 10 to the 20, 28, 29 flops, which ends up being gigawatt facilities running model training cycles for months and months and months. Like it is an enormous scale.
Yeah.
But fundamentally, what are these models, right? Like what are these LLMs? They're autoregressive models. They're taking, basically history of text and then trying to predict the next token, in many ways from, left to right generation process, right? And so is that actually intelligence? Like, are we actually, creating, intelligent machines when we do this? I mean, the perception, I think, to humans is, well, clearly they're intelligent. They're spinning out, incredible solutions to problems. But all of that has been trained on human data, this incredible massive corpus of text that now has existed on the internet. But is that actually the future of super intelligence, right? Like, I would argue that, when you think about what is intelligence and how do you define intelligence, you're sort of saying, there's this agent or an entity that's taking actions, receiving feedback, trying to understand the environment that it's in against some goal, right? And and this is where I think it's hard to say that the future of intelligence is going to exist in the data center medium, trained on large scale corpuses of human text that have existed in some ways in the past, right? The future of superintelligence, in my opinion, is this sort of reinforcement learning approach. If and there's Richard Sutton actually just did a wonderful blog post and interview on this, where you really look at reinforcement learning as an approach that needs to be scaled out into the world. Well, if it's out into the world, then what is the infrastructure, one, that's going to enable us to get out into the world? This process of continual training and continual learning. Software needs to power that. Hardware needs to power that. And then you get into like the physics of heat thresholds and thermal layers and, all of these, just even battery capacity out in the real world to actually have a constant training and learning process that occurs, in reality, not in a data center. And so, I sort of feel like that today we are working towards systems that have a very strong economic reward. There's no question that what has been built so far is incredibly valuable. We see this in code generation and many of the use cases that have become commercially valuable. But I don't necessarily know that like training training models and continuing just to build our gigawatt, facilities, to continue to have this perception of intelligence in regurgitating, a lot of, history of human text, particularly, and even I would argue even in video generation and image generation. I don't believe the models understand what they're actually doing. And hilariously, we actually don't understand what these models are doing. And I think,
Yep.
Dario
Well,
Amodi has written some wonderful, essays on, mechanistic interpretability and understanding, how do these models work. But if you step back, like as as engineers, what other part of engineering as a society would we be comfortable with structuring and using products when we don't understand how they work? Like if you go to a structural engineer and you say, "Is that bridge going to hold up?" Well, would you be
There's a
comfortable if
probability it
the
will.
there's a
there's a
probability that
probability.
it will, and we certainly hope. I certainly believe that it should, but I don't know if it will. Like that
I did a
seems.
demo where someone drove a car over it. It didn't break, so therefore,
Yeah.
everyone can drive on it.
Yeah,
It's
and
fine.
I have a question
and
for
I
you,
hold
Tim.
little, I hold concern there. I guess I would say I do think perhaps we need a different approach, and I'm not in any way suggesting that I know what that approach is, but I often wonder, are we on the right vector? Um, and humans have a nature of just trying to go to the simplest path on things, and sometimes I think we do need some more contrarian thinking
Yeah.
in innovation, particularly in this space.
I can't help but wonder if LLMs aren't like the CPU. If you think of AI as a computer, as we're bringing in memory, as we're bringing in tool use, as we're bringing in multimodal capabilities, as we're bringing world models into the picture, as they start training on things like the mountains and mountains of corporate data in the world that is sitting locked in databases right now, and even the possibility of what kind of data are you getting back from AI wearables, from electric cars, from what's Google Maps collecting. I mean, I feel like there's probably an interesting amount of data that would be really boring to read, but might do a lot in giving these things a little more of a perspective, almost a worldview. I'm not necessarily talking about consciousness. I just mean in terms of fleshing out the bits that were originally just an LLM and going from there. Do you feel like that is a possibility, or do you think that's the wrong direction?
I think what is likely, and I know, even back at Google, I think this was a thesis that we had, back in 2017, 2018, was, look, at the end of the day, distillation is now, an incredible process. This was, something that had been invented earlier on. You have these massive models, and they have this incredible sort of history of human knowledge contained in them. But again, if you just take that and you put it out into the real world, it's not like it has an understanding of, an object, if it's occluded, that it continues around, the entirety of the object, right?
Yeah.
Just like when children are first born, they recognize physical concepts pretty quick. They don't need to be trained on some historical corpus of data. And so you ask, like, is it like a CPU? I think it has to be more powerful than a CPU. I think there has to be some generality to to the infrastructure, no question. But if you look at where we are today in AI, in some ways, with GPU capacity and how fast it's been scaling, I sort of in some ways believe it's reminiscent of like the first sort of foray into cloud infrastructure. There was one major provider at the time, that was AWS, and everyone, first, traditional enterprise was like, we would never go to the cloud. You would be crazy to put your data in the cloud. You fast forward a decade, now it's like, not only do we want our data in the cloud, now we want to be multi-cloud. And so, I think your analogy is interesting, but I think the actual inferencing process and the speed at which it has to happen and the latency at which, meaningful results have to return to the user. And, there's a quoted statistic that we used to use in Google search was, for every 100 milliseconds of latency, it was 1% in revenue. And I think that's been validated also by Amazon. So in the real world, like if you think about deploying just on a CPU, for example, in an autonomous vehicle, could you imagine flying down a freeway and, I don't know, a ball floats out onto the freeway, and because the CPU just is not as powerful as a large, parallel, just in terms of flops and processing, the car will have hit the ball and be another 2 miles down the road before you get an inference response
That is
that says,
correct.
"Watch out for the ball," right?
Yeah.
Um,
Like imagine
and
if it
so
had to
that
go back to OpenAI in the cloud and come back before it could
100%, right?
react.
And I think that's the practical the reality, though, that any future system, any future form of intelligence needs to be able to have, and I think we as humans have this sort of biological process that we've inherited over generations, but it is incredible that we are able to process so fast and respond so quickly to things. And I think
Yeah.
computationally, a CPU can't get us there. So then the question is, in the real world, I don't know if you've been in a Waymo,
Not
or in
yet,
a,
but I
an
hope to
autonomous
this
Tesla.
month.
Yeah,
Yeah, I
they're
mean,
cool.
they are marvels in the sense of, and we can talk about all the different the sensors and the different approaches on those sensors on those vehicles. But at the end of the day, you do need a degree of processing power against some battery capacity and thermal thresholds
Yeah.
that enable intelligence to respond quickly, because everyone, I think, is optimizing now for a high degree of perceived intelligence at the fastest possible outcome. And I think it's actually the nature of, you know, uh, consumer behavior over time because of internet products that have been, created over the last 20 years. And I think Google is obviously a big leader there, but that's not to say that Amazon and Meta and other organizations haven't done incredible work. But what we have done is train everyone to get everything instantly. And
Yes.
so, even now, we introduced thought reasoning on these large models like ChatGPT, and, DeepSeek obviously was a big provider of it. But now it's funny that, like, you sort of sit there seeing these things think, and you're like, why is this taking so long? And it's just an interesting observation that, everyone now wants things even faster. And I think that that's fine when you're connected to a high, particularly in the Western world, by the way, when we're connected to
Yeah.
high speed bandwidth, fiber connections, and you can get information piped back to you very quickly.
Yeah.
The world becomes very different, though, if you've traveled to India or other places where the
Even
network
parts of
quality
Europe.
is poor. Well, I mean, I would argue even, I'm a dual citizen of both Australia and the United States, and there are plenty of areas in both countries, frankly, where I feel like I'm back in dial-up, the original internet sound, just trying to get some data onto my mobile phone. So, there are still a lot of, physical challenges that exist in executing AI out in the real world.
Yeah.
And I think, this just goes back to the point. I think we do need the ability to have a unified compute model, because it's not just going to be one type of silicon that gets us true superintelligence. I think even if you believe in a construct where there is a large world model that is being trained on huge data center capacity that we're rolling out, both in America and other other countries around the world, I think at the end of the day, you want to distill that down to some core knowledge corpus, and that model may end up being a billion parameters, 2, 3, 4, 5 billion parameters that resides on an edge device that is continually training and continually learning in the environment where you are. Because if there is anything, true about technology, is throughout its history, it always moves closer to the user. It always has. Now, the medium we have settled on, thanks to, Steve Jobs and the wonderful folks at Apple, and then obviously that's proliferated across many other countries, is the
Mhm.
phone.
Yep.
But is that going to always be the device that has the highest I/O threshold for us? I don't know the answer to that.
Same.
But I do
I
know
think
is
empirically, no. We just don't know what the next thing is, in my opinion.
right.
Yeah.
And it's so funny because it's the fickle nature of human beings, both from a perception of what's cool and what device do I actually want around me all day long,
hmm
to what provides me a high enough degree of utility that I'm actually willing to invest in this platform. And I
Right.
was one of the I had Google Glass early on, um, and when it was very because I worked at Google on TensorFlow Lite, and it was just a weird it was a weird social interaction to be wearing glasses and then sort of be like looking up to the sky when you're talking to someone. And it was sort of a little bit like, what exactly are you doing? Why do you keep looking up at, like, off to this region in space and then coming back
Right.
and talking to me again? Clearly that's not going to work, right? Like, that's not a social
Yeah.
medium that works. And I think it will be interesting to see, even with the evolution of glasses as a product, how do you get the consumer interaction? How do you get the experience good enough that people want to believe that the utility is there To have that, and fundamentally my point is to have that as an input device of what is happening around, around a person to improve AI. Because the more that we
right.
can get AI out into the real world, I think the more that it will be actually be able to be closer towards intelligence. It will be able to perceive, it will be able to
Yeah.
understand complex environments and then respond to some goal. And I think that's what we're lacking in today's systems.
Get it walking around in robots and kind
I mean,
of
that's
checking out
that's
the world. Yeah.
yeah. I mean, I think that's that's an interesting, that's sort of in many ways an interesting frontier, because you aren't in that you are so limited in that world, and you have to make constant trade-offs between, if I tune and deploy a more powerful model on a robot, then I know I'm doing that at at risk of using more energy,
Yeah.
which reduces the utility to the end state consumer. That's like, again, I want to plug in my my
Yep.
iPhone and get 5 days of battery. I don't want to plug in my robot and then 25 minutes later it's like, sorry, I've run out of power. I
I'll
would be
finish
like,
your
Right.
laundry in 4 hours. Yeah.
100%. Why did I pay $50,000 for this robot that I need to charge every 10 minutes? Like, that's not going to fly. And
Yeah.
so there is
Right.
going to be an interesting balance there. And a lot of it, not only is it hardware innovation and silicon innovation, a lot of it is like, what is the software model that's going to power that to enable developers to move quickly and iterate fast?
Yeah.
And so I think
So
that
are you
is
working on
very
that
much
at
is
Modular?
ambitious.
Are you actually building like software to work on these edge devices and robots and all this sort of stuff?
Yeah, so how we, I can talk a little bit about our platform. So how we started was we recognized at Google that one of the biggest challenges is that most software that people interact with today is built on top of what hardware manufacturers build for their chips. So at the end of the day, you write a program, it needs to map to the silicon that it's executing on. But the challenge is every hardware manufacturer comes out with its own stack. So,
Mhm.
NVIDIA has CUDA, AMD has ROCm. I mean, you could go through all the different silicon providers.
Yeah.
So where we started was to say, is there a world where we could build an independent software stack that enables us to bring up hardware without needing to rely on the vendors, libraries and infrastructure? And so that was sort of the big challenge. So one of the things we built, and I say this lovingly, that Chris Leitner, my co-founder, he doesn't need much incentive to build a new programming language. He loves, I mean, this has been in many ways his life's work. But so what we realized though was the problem was there a way to build an abstraction where we could essentially write programs that became portable by nature? And there's there's a lot to that. I could go into more detail, but fundamentally the concept is, could you write software, particularly AI software, very low-level operations that would enable you to go across different types of hardware easily? And so we
Kind of a
we had some infrastructure
translator, sort of?
yeah, except it's a brand new programming language. So we actually rely on some technology we built at Google called MLIR, which
Okay.
stands for, and this is might go too low level, but stands for multi-level intermediate representation. So it's
Okay.
about building a representation of a program that can go across different types of silicon. And there's methodology behind that, and I can spend time talking about it. But
Yeah.
but fundamentally, the goal was enabling our engineering teams to be able to write high-performance kernels and low-level operations that could scale when AI models execute across different types of silicon. So we started building that, and we also started building it in a way that was heterogeneous. So what I mean by that is, we believed from our infrastructure work at Google that the future was going to be lots of hardware interacting and different types of hardware interacting with each other. Part of this was from like I talked about the mobile experience. You have 4 different types of architectures on a mobile phone. Ideally, you want them all working together. You want them all
Mhm.
humming together.
Mhm.
Well, again, if you don't have a programming model that can actually program all 4 different types of accelerators, that becomes really hard. And so we said, well, let's create this new programming model that makes it easier to actually program, for example, a CPU and a GPU together. If we could do that, that's like stage 1 to getting more utilization, more efficiency out of the hardware. And the big challenge in doing that was, cool, but could we meet the performance of someone like NVIDIA on their own silicon? Is that
Yeah.
is that possible? Because if we couldn't achieve that, from a commercial standpoint, from a business standpoint, no one in the world is going to be like, wow, I love your idea, but I lose dollar per
Yeah.
per token per watt
Can't
using
be
your
great
stuff
and
versus the other.
lossy. Yeah. You've got
100%. It's just not possible. So we started by doing that, and that's low level. It typically is for more advanced programmers. But we are sort of working on that programming model evolving. And then on top of that, and so you can think of Mojo and that the programming language called Mojo, you can think of that as a comparator to say CUDA, which is a low-level programming model for programming GPUs. The primary difference is we can go across any type of hardware, not just not just GPUs. Then above that, one of the things we realized at Google, and this is sort of a long-winded story, is we realized we needed to build essentially a new AI framework. And we call that Max. It is a modeling and serving framework. And so really this was carried through all of the lessons and the mistakes and the learnings that we took from, building TensorFlow as a high performance, AI framework. TensorFlow now has sort of fallen off in terms of popularity, and you have PyTorch and other things. But what's interesting and what we realized was, I'll go back to one of the comments I said earlier. We realized we needed to build a framework that could realize this vision of what you train is what you serve. And back in 2017, 2018 at Google, we saw the inference training flip. We saw it all the way back then. And it's a funny story because when we first went out and started pitching to get capital for Modular, a lot of the investors that we pitched to were like, yeah, no, inference is the thing. Inference scales to the size of your user base, training scales to the size of your research team. I assure you, inference is going to be the thing everyone wants to focus on. And we were, I won't name names, but we were told at the time, oh, that's wrong. Everyone should be doing training. You should be focused on training. And we were like, yeah, I think training is going to become a lot smaller. It will still be a very large workload, but the number of people doing it will actually regress quite significantly. And look, we obviously had a thesis, and other people had their theses too. But that turned out to be somewhat correct. And so what we realized was, today with PyTorch, if you build a PyTorch model, you can't actually deploy that at large scale in production, and that's why open software today like VLLM, which is an open serving framework, it got created to essentially help fix the problem that PyTorch can't actually serve large scale production workloads natively, right? When we created TensorFlow, it was the other way around. TensorFlow was wonderful at large scale inference and not that great at, particularly from a usability standpoint, not that great at training. PyTorch was incredibly great at training, but not that great at inference, right? And so what we realized was, well, there's going to be an opportunity here to build a native framework, a new framework, and it's open source, where it starts with inference, and we could do large-scale inference, and we can do large-scale inference across compute types, and then we can add training actually easily enough. And the beauty of it is, it has a serving component to it natively. So you can essentially run open models, all of the popular open models that you would otherwise be aware of. You can serve them. So now you can actually serve these things on, increasingly we actually last month announced Mac support. So running these things locally on devices like Mac machines, but then also taking that to very large data center workloads, right? And so at that point, what we realized was, hey, look, we have an opportunity here to really take a lot of our knowledge in AI framework design and build a new framework. And then above that, increasingly, I will say that AI is now a full stack. It's a full stack challenge. I certainly believe that inference is almost in many ways more complex than training at scale now. It involves, increasingly at the Kubernetes, particularly the Kubernetes style layer in the stack. You have, this idea now of splitting out prefill and decode components of the transformer architecture. You have different ways of managing caching and prompt caching, and how you do that across all sorts of different models and all sorts of different hardware. And so what you end up needing is, essentially a solution there too. And that, today we call it Mammoth, but fundamentally that's going to become a cloud, part of our cloud offering. And for many developers, our goal is just, look, we can serve across hardware. This idea of, talking about analogies, Corey, we love to frame the unified compute model really as like a hypervisor for compute, right? If you could log into a platform and you could just say, here's my throughput, here's my latency, here's my, how much accuracy I'm willing to reduce through methods like quantization, and here's my cost target, just make it work. Like when I log into Snowflake, I don't execute a query and then go, oh, well, what CPU machine did Snowflake choose to execute my query? I actually don't know. right?
Right.
Well, AI should be similar, certainly at least in the cloud to start. Similar. You should be able to log into a platform, just give your requirements, and expect the best TCO for your workload. Like the total cost should be highly optimized to whatever those parameters are, and
Mhm.
software should figure it out. It should be that
Yeah.
simple for developers then to go off and build applications. And that's, Grant, hopefully that answers the question of, what are we building
Yeah.
at Modular? That is very much what we're building.
So if I was a developer and I was building like a robot, right, for example, or working with robots, I could use Modular to run if I was using like a specific GPU or whatever on my robot. I could use Modular instead of CUDA.
Yeah. So today the open infrastructure we have is the framework. So Max and Mojo, which is the programming language. You can just go to our
Right.
website today, download that, start playing with it. You can write operations for custom silicon. You can write your own machine learning models and scale them on robots if you want. All
Cool.
of that is available today. We do work increasingly. A lot of enterprise customers that come to us are still of the belief that like we want data center specific AI at massive
Mhm.
scale. And so of course they are looking for cost gains and performance wins. And so, one of the key custom, I mean, we're working with a lot of customers now, but one of the, the sort of testimonial stories, we worked with an awesome company called InWorld. They're like an advanced,
Yeah.
originally gaming, but now doing like an AI runtime.
Right.
So it sort of metricizes and can do runtime environment for you in your the applications. And they came to us and said, "Hey, look, very advanced team. They're all ex DeepMind, and they said, look, we're using all this open infrastructure of LLM and other things, but we need here's our use case. And again, to reiterate, this is how people approach what they're trying to solve. It's we have a text to speech model, and we want to get the first 2-second audio chunk back to a user in under 200 milliseconds.
Yeah.
Is what we want to be able to achieve.
We've played
right?
with their
So
model even.
Yeah.
Right.
We know
Yeah.
exactly what they're trying to solve for.
And so the challenge they had was, as you scale throughput, the latency explodes. So the problem is, as more and more users come onto their system, those concurrent requests each one ends up getting higher and higher on the latency threshold. And so, it's really interesting. There's a couple other customers that I can't name yet, but there was this really interesting user observation in that, right? And what the user observation is, irrespective of how intelligent a model is, if the latency threshold goes up, an everyday person interacting with AI thinks the model is dumber.
Yeah. I was thinking that was what it
And
was.
so-
Yeah.
Right. And so what that means is that as a consumer of technology, you're sitting there and you're like, if it's a text to speech model, you're saying, maybe it's a nursing agent or a healthcare agent, or there's something going on, right? And you say, it rings you up or does whatever, and it says, hey, how are you feeling today? And if you say, oh, well, I'm not actually feeling that great, and then 10 seconds later, the model goes, oh, well, that's no good. You're like, this the person I'm like, what is going on with the person I'm
And
speaking to, right?
it feels very like that. The every second delay with a speech model really
100%.
makes a difference when you're
On
It
the
really makes
consumer end,
listening.
especially,
Yeah.
that's where it's really, really noticeable. It's like,
Yeah.
please
Like,
sit
if I
here
have to
while I go
wait-
retrieve your information. I'll be back
Yeah.
momentarily.
Yeah. If I have to wait for ChatGPT to talk back to me, I'm like, I'm just gonna close this. Like, it's not.
They've come a
I'd
long
rather
way.
read it.
I
Yeah.
will say they've come a long way. I spend a lot
They
of
have.
time working with those models, and even ChatGPTs, Groks, Googles, even Claudes. They were all fast, which is a thing
Yeah.
that's been impressive.
getting
Because
that.
when it first started, it was not that way. When they first started
No.
releasing those models, it was like, and it was mind blowing, even though it was 10 seconds.
Yeah, and I think the challenge is you get these awkward, you sort of go to speak over it, and then it sort of tries to stop, and then you're like, oh, even in our conversation, and I apologize in any way if I interrupt you guys, but if you go to talk and then I go to talk, I'm like, oh no, Grant, you go, or no, Corey, you go, and so there's this weird back and forth
There's
interaction, and of
There's
course,
the latency of the human brain, and then there's the latency of we're doing this over streaming. So there's the latency
Exactly.
of the
Yeah.
streaming.
Yeah, the
recording as
internet's
well.
still a
So-
factor. Yeah.
And so it's wonderful to hear those stories because at the end of the day, like, infrastructure is a tool, and you
Mhm.
want to understand, but how is this actually impacting, what you're trying to build, and really understand what is the application, what is the end state. And
Yeah.
so for them, using our infrastructure on, they were deploying on Blackwell machines, which is,
Hmm.
incredible piece of silicon from NVIDIA.
Yeah.
Um, we were actually able, for them to 4x the performance over VLLM,
Wow.
and ultimately, reduce their cost base by, I think it was 60 or 70%. And so,
Wow.
why does that matter? That matters in a few ways. One, penetration of technology. Because fundamentally, if you can lower the cost threshold, then
Hmm.
it becomes a lot more. It's easier for people to try it and adopt it. And I think they're now 20x cheaper than than their competitors in the TTS space.
Yeah.
But more
Wow.
importantly, it begins to map and make those interactions more real, right?
Yeah.
And this is not to say that a TTS model is in any way intelligent and understands what it's doing, but the use cases become more powerful because
Yeah.
I still strongly believe. There's some incredible companies working on things like preventative medicine and being able
Hmm.
to call American citizens just to check on them, and to be able to say things like, "Hey, look, did you take your pills today? Are you feeling okay?"
Yeah.
And if those responses can become more intelligent and, we can help people in their everyday life by deploying that type of technology, in a real-time fashion at scale, I think that's, that makes coming to work every day worth it.
I want to kind of like zoom out a little bit here because we have seen all of these really incredible deals announced recently between OpenAI and like every chip maker that I know of. They've got
Yeah.
deals with NVIDIA, they've got deals with AMD, they've got
And
deals with
NVIDIA got a
Broadcom.
deal with Intel in the middle of that. Yeah.
Yeah, like there's all of this stuff going on. And NVIDIA is, from my understanding, a partner with you as well. Is that correct?
Yeah, they are. I mean, we're trying to partner with all the silicon providers. I think at the end of the day, what we're really trying to help unlock is, it would be wonderful to see a lot more competition in silicon fundamentally. And
Yeah.
if
Mhm.
software is what is restricting us, um, I just think there's so many problems to solve in the world and so much innovation that can happen there.
Hmm.
And so, our belief is by having a unified independent compute platform, we can help other, new startups in the chip space accelerate faster and sort of adopt our infrastructure and move quicker to meet customers' needs.
Because my
I would.
understanding is that NVIDIA's CUDA is like kind of like the reason, like, yes, their chips are the best right
Mhm.
now, but also CUDA is really what keeps people locked in to working
Yeah,
with
and
them.
you can look at the history of it. I mean, it's now a 17 year old platform, but I would certainly say many of the decisions that were made at companies like Meta and Google to build these AI frameworks on top of CUDA, as a programming model for NVIDIA's acceleratable compute, really acted as a massive distribution mechanism for them to get very mass scale, right? Like
Mhm.
Yeah.
it accelerated the adoption and penetration of execution of models on NVIDIA's hardware. And if you look at
Right.
other folks, like at the time those decisions were made in frameworks, like TensorFlow and PyTorch and others, it was the best thing around. And so
Yeah.
people went, well, let's just use that. But by doing that, they obviously changed the trajectory, certainly for NVIDIA, and I'm sure many happy stockholders at that company. But
Sure.
also, more broadly on how other companies can come and compete, right? And
Yeah.
so I think a lot of what we fundamentally believe is not only is a unified compute model good for penetration of applications, both at the data center and the edge, it's also good just for competition. It
Yeah.
makes it possible for more people to compete, and that, there'd be more innovation at the silicon side of it. But Grant, you also asked, all of these deals and
Yeah.
all of this sort of circular money flow.
Right.
I think there's been parallels drawn, and there's a guy, Tomas Tungs, who's a former VC, and he has a blog. And he has a wonderful blog post on this, sort of comparing it back to when we were laying fiber back in 2000s. And I think the difference, of course, now is I don't I think that GPU utilization around the world right now, most GPUs, are probably running reasonably hot, given
Yeah.
that the amount of AI that's being consumed. I think it is a very different time to what was happening when we, certainly in America when we were laying fiber,
Mhm.
and it just wasn't being utilized yet, right? And then
Yeah.
of course,
Right.
across the arc of 20 years, that's changed.
Yeah.
But I think, you need to look at there is significant revenue consolidation on who is paying. You always look at where is the money coming from, right? At the end of the day, the money is coming from, essentially the Magnificent Seven technology companies, which represent roughly, I believe, 30% of the S&P 500 in terms of market
Yeah.
capitalization.
Right.
So, if they're the ones buying all the compute, you would have to look at their businesses in the long term and say, is that sustainable? I think the challenge, of course, is at least at that level, they're also building all their own chips. And so,
Right. Yeah.
in many ways, there's this purchasing of additional capacity from companies like, OpenAI. But then, it's been interesting to see in the media that OpenAI is also now trying to build its own silicon.
Yeah.
And
Correct.
traditionally, that's what you see, right? Like you see, and I think this was true even at Google. You start with sort of models, and you train models, and then what you do is you go up the stack and you go up into the cloud, and you say, well, now I need to get mass distribution for my model and prove that this is a compelling set of technology that has vast user adoption and that is economically viable. And then you prove that there's large revenue generation,
Yeah.
and then very quickly you're like, now I need to go down because I need to figure out how do I get better cost optimization across the silicon, right? And so
Yeah.
I think and obviously OpenAI has been the most famous on this. You could compare it to Anthropic with
Mhm.
with Trainium and their relationship with AWS in a similar way. But a lot of it is just this constant belief, and I think that I do personally think that we are right to challenge it. That is the future of superintelligence just continuing to scale these models larger and larger and larger and larger? Is that actually getting us on the path to some form of superintelligence, or is it not? Because we are spending an enormous amount of capital
Yeah.
on the belief that it is, and there may be utility there. I'm not suggesting that there is not utility in that investment, but I do agree deeply with Jan LeCun and Richard Sutton and others that have made the case for, look, autoregressive LLMs is not actually the path to superintelligence. We need a different form of innovation. Like I was at
Mm.
Google when Noam and Aidan and others created the transformer and intention is not enough, and it
Yeah.
changed the world. But are we convinced that that's the final architecture and that that is reflective of what we see as intelligence? I personally am not convinced, and I think it would be great to be able to see a different approach. And so the sloshing of all the capital is highly, is predicated on this future of just keep scaling the flops,
Yeah.
and keep building the data centers, and maybe that's a viable path. But I
Well, I
do think
guess I
it's right to
wonder.
question it.
I wonder though if it's not like because eventually you'll have to scale whatever the current architecture is in theory, or sorry, well you'll have to scale whatever the architecture is that works. If you're following the bitter lesson, which for people who forget what that is basically like if you have, basically reinforcement learning scaled properly is like just all you need essentially. That's a very
Yeah, search and
just
learning are really the primary techniques of being able to scale the future of these models. Sorry, Corey, you were about to say
Oh,
something.
yeah. I said, I even feel like the reason the jury is still out for me is because I feel like what we're watching right now is this certain amount of concentration in smaller models. However, that's largely fed by this idea that we're going to scale this up bigger and then we're going to work to make it more efficient. We're going to work to streamline it. We're going to make it faster. We're going to make it smaller. And this idea that, smaller models are getting better. And there's a big focus right now, at least it seems like to me, on better data, cleaning data, training models on increasingly better data. So I don't know, does scaling have to continue being able to push these smaller models up the food chain as well? I don't know, but it's sure fascinating and a lot of fun to talk about.
Yeah, and I think even if you look at humans, right? Like I'm in no way a neurologist, but I do know that we don't execute the vast majority of our brain function when we operate in the real world. And so
Yeah.
again, this comes back a little bit to the idea of um, you know interpretability and actually understanding why do models make certain decisions at certain points, when different neurons are firing inside these model topologies.
Yeah.
We don't understand that yet. So for all we know, much like the human brain, the vast majority of these models, these models' weights, which represent its pre-trained in-weight memory, maybe it's just wasted. Maybe it was always interesting when sparsity came out and pruning and quantization techniques came out, and you could chop large layers of models out, and fundamentally it still worked very well.
Yeah, and
Right,
you're still at
right.
like
And so
97% or
right.
something. Yeah, there's a
So
loss, but it's minimal.
so are they breadcrumbs towards, well, maybe there's a different approach here that's needed? And I think to your point, Grant, yes, maybe in one school of thought, I think it's correct to say that we could keep training, but maybe in a different school of thought, I think we can certainly question, well, is there a world where you have a very small, but, to your point, Corey, high quality model that has a incredible rich architecture that actually answers the vast majority of what we need it to answer
Mhm.
in how we perceive intelligence to be able to scale and navigate and understand complex environments to achieve some goal. I'm still on that, increasingly leaning to that side of the fence, and I don't necessarily know
Mhm.
how we get there. But I
Yeah.
don't think I think that we don't know how to get there because yet, I still can't sit here and say we even understand how these models work. So I think that,
Right.
Or
you
our
know,
brains, for
it,
that matter, in a lot of ways.
that's right. And so I think, I would love to see, and I say this in an article I wrote, I would love to see a much larger percentage of capital flow from, or certainly, OpEx flow in these large frontier labs towards, interpretability and research on,
Yeah.
interpretability. Because I think, just the basics of engineering, it should be that we understand, like we're deploying a technology at mass scale, and yet we don't understand that technology. And I just think when you apply that to any other construct in engineering, I just think people would fall over and say, oh, that's crazy. Why would we do that? We're not going to go and build a bridge and just hope, we're going to send a whole bunch of traffic over it and hope that it stays up.
Yeah.
I think most humans' perceptions of risk would be, well, I'm not driving over that bridge.
Yeah.
And yet we're rolling out and penetrating this degree of infrastructure in society without clear answers. And I think we owe it as an industry, but we owe it as we owe it as, in many ways, we're creating, we have the ability as a species to be creating our future incarnation of what's next. And I think
Yeah.
we owe it to ourselves to deeply understand that.
So 5 years from now, if modular succeeds at its mission, what do you think the AI infrastructure landscape looks like? With the caveat that we know that there's going to be this big kind of like shift where it's like either scaling works or we have to come up with something different. So we've established that that's a
Or we're
paradigm that's
still asking the
unknown.
same question 5 years from now.
True, it could be unanswered, I guess, by then.
Yeah.
But what does modular look like? And
Yeah, I think there's a couple of ways to answer that, right? Like, we certainly hope that the open infrastructure, so Mojo and Max, gets penetrated, across the development community and development ecosystem very broadly. We think that, it is open source. We would love the community to rally around it. It gives people more optionality. I do see it as, the future, and again, in my opinion, as I understand it right now, is a lot more contingent on reinforcement learning and really continuous learning. And I think to achieve that, we need software that enables us to, one, really take advantage of all the compute in the world. I don't believe we're doing that today, as crazy that may sound to some people. We need to be able to fully saturate and utilize the compute. We believe we're building the framework to do that, and we would love people to adopt it and be able to realize, go and build incredible applications and invent the future with it. So that's one thing I definitely think we want to see. I think the second thing we want to be able to see is, as a company, we have and absolutely need to scale and are doing this now very significantly, just the commercial side of our organization. Our vision for Modular is to remain an independent company. And to do that, you need an enormous economic engine. And I think the currency of the AI industry is, essentially dollar per token. We believe that we can provide efficiency gains there better than anyone else. And we believe that, now a decade helping build AI infrastructure, of which I will both apologize for, because a lot of it has been messy. But we've taken those lessons and really tried to invest in fixing those mistakes, in building a new platform. And I think, for more, certainly at least at today, and Larry Page, when we're at Google, had a famous saying of, develop for the most sophisticated developer today, because that will be everyone tomorrow.
Yeah.
And
Mm,
today that's us.
I like
we
that.
are very much in the advanced user cohort, but 5 years from now, I would hope that diffuses more broadly across
Yeah.
enterprises, and it's just easier, and they have more optionality, and they're able to do more with AI, than ever before, both in the data center and at the edge. And the last thing, certainly that we would hope for is that there is more diversity in silicon. I
Yeah.
think, I've always believed markets are enormously power law distributed. I think you can look at any of the Magnificent Seven today, and you could argue in their own individual right, all of them are monopolies. And I know that, that's probably a scary word to say for some people, but the reality of the market is there is enormous market power in each of those verticals. And so, being able to have more innovation down to the silicon level and see entrepreneurs go back to, the raw atoms and physics of being able to move bits around more efficiently and be able to build silicon and tape out silicon and innovate in that space would be something that's incredible. And I think, what we're hoping in our platform, particularly as, more developers adopt it, is that then it's easier for hardware manufacturers to come on board and use it. And the analogy we try to apply there a little bit is similar to Android. Like, Android did a wonderful job of being an open ecosystem. They helped unify a lot of the handset manufacturers to be able to have an operating system that was a different approach to Apple, but enabled them to compete in an ecosystem that then helped really now cover half the planet
Yeah.
in terms of phone distribution. We hope that there's a software layer there that makes them being able to plug into and compete quickly out of the box, that that drives more innovation there too. And really what that achieves at the end is the best product should win. I've
Yeah.
always believed that if you can build tools and you can build infrastructure that act as a great equalizer, and at the end it drives more innovation across technology, that's a net positive for the world. And lastly, I'll say, I certainly hope that superintelligence is created on the modular platform. I mean, we would.
Of course, yeah, of course.
I strongly subscribe to Jeff Bezos's regret minimization framework, and I really do believe
That's funny.
that you can look back in on your life, and I think if AI has really helped to penetrate a society and generally make it better, which I strongly believe that it will. And there's a lot of risks and there's a lot of challenges, but that's true with any new diffusion of technology
Yeah.
as it penetrates society. And so I think our vision there is if we can help leave that small dent on the world, and enable people to adopt this technology in a way that's beneficial, that would be an amazing life to be
Yeah.
able to look back on. We still have a long way to go, though. I would say
Sure.
that.
What's the easiest way for someone to try out modular without committing to a massive infrastructure migration or
Yeah,
something?
it's free to try. Just go to modular.com. You can click Getting Started. Great tutorials and getting started guides. We support an enormous number of open source models. We are bringing up sort of the endpoint cloud solution that will enable developers just to start serving models really easily out of the box. But today, right now, it's been more a focus on, you can download the infrastructure and play around with it yourself. We have a bunch of instruction markdown that enables you to easily punch out some code with the help of those tools. And so we're a startup. We're like a hummingbird. We're extraordinarily responsive. And if you you can join a forum or a Discord or just ping us on social media, and we respond as fast as we can. And we believe that we're building against what people are asking us to build. And so for us, it's just come and join the mission and help us change the world.
Do you think that it's easier to build on modular now than it would be on PyTorch if you're a total noob?
I think now, we've done a lot of the legwork for serving. So we are still an inference platform. I think PyTorch is still wonderful as a training platform, and the team at Meta have done a really incredible job there. I believe our vision, though, is to actually in the long term to make people's lives easier. Like, when you deploy a container today with VLLM in it, you have to download one for NVIDIA, and it's about 10 gigabytes. if you download it for ROCm, which is the AMD platform, I think it's like 20 gigabytes. Well, we have a single container that can execute, across both those platforms now that's under a gigabyte. And the reason for that is when you rebuild something, you scoop out all the dependencies, and you basically then, reduce the overall footprint. And why that matters is, when you think of cold start time and you're deploying on Kubernetes instances and you need to scale these containers all over the place, like every bit counts. Like
Yeah.
it really does. And so, our goal is to get there, Grant. There's no question. The only way we're going to get there is with a motivated group of people. But we do have a lot of knowledge that I think we want to impart on our platform too.
Yeah.
But at the end of the day, any platform is a function of its community and the people that choose to invest in it. And so we're very, very conscious of that. I think it's something we're committed to investing in. So I would challenge folks out there, if they're excited about AI infrastructure, come and give it a go. If you run into some challenges on what we're doing, be loud about it, and
Yeah.
we will help. we will respond as quickly as we can.
That's the stuff you need to
how
know, right?
exactly. Yeah,
Well,
exactly.
Tim, thank you so much. This has been a great conversation. I really appreciate that you took the time to join us.
No, it was lovely. Thanks so much, Corey and Grant. This was a great discussion. I appreciate and apologize. We traversed the map. I feel like a little bit in
I love it.
in the surface area of what we touched on. But
We
yeah,
did.
I really appreciate the discussion and and thanks for having me on the show.
Well, thanks so much to everyone watching. We really appreciate that you took the time to join us. Please like and subscribe to the channel so we can continue to bring you more great guests like Tim. And overall, thanks for watching. If you haven't yet, make sure to pop by the Neuron.ai and sign up for the Neuron AI newsletter. Join about 600,000 others who get it every morning. And until next time, farewell, humans.